Okay, so what we're doing today on this video is more examples for 1.1, so more 1.1 examples. And so let's get to it, paper view. And so it says determine whether the curve of the graph of the function of function of x, I'm tired, if it is, determine whether the curve is the graph of a function of x. If it is, state the domain and the range of the function. So our thoughts when we're given a graph and we're asked whether or not it's a function is the vertical line test. And so I start thinking about vertical lines and only hitting the graph one time. I know that it might be hard to see, so I'll even zoom in on it a little. Maybe that even makes it a little bit blurry. Are you going to focus thing? Because sometimes it'll refocus. It's not doing very good on its focusing there. So, but if I draw vertical lines right here, I'm only hitting the graph one time. I wanted to zoom in on this because that's open and it's closed here. And so if I draw a vertical line right there at -1 at -2, I'm going to hit it one time right here, but here it's open, so I'm not hitting it here. If I draw a little bit to the left of that, then I'm hitting down here. If I draw a little bit to the right of it, then I'm hitting there. And so the story is, I went the wrong way, sorry about that, don't get dizzy on me, is that that here it is the graph of the function. It only hits it once, only hits it once, right, all the way through. And so to the question, is it a function? I'm going to abbreviate function, FCN, and I'm going to say yes. So they told me that if it was the graph of a function, then what I needed to do is I needed to state the domain. So the domain is the x's. And so I like to think, okay, well, the furthest that I go ever to the left is here at -1, -2, -3. So for the x's, the furthest I ever go to the left is -3. The furthest I go to the right is +2. So that my function, if I just go from -3 to +2, I have the whole function is trapped in there. Okay, now I want to know, does it leave any values out? And the only place that I'm wondering whether it leaves any values for x out is right here where that situation happened. But I see that if x is -2, it's defined to be, the output is defined to be -1 right there. And so actually it doesn't leave any values out. So the domain goes from, what did we say, -3 to +2. And it includes the endpoints here. The endpoints are included. This graph came out of Stewart, and it does have the endpoints with a dot on it. Remember, we saw in class in 1.1 a graph that came out of Stewart that did not have the dots on the end. I was telling you that he sometimes can be a little bit not that consistent on his graphs. Now, the other thing I want to look at is the range. And so when I look at the range, those are the y's. And so I'm thinking, well, how low does the function go? And so how low the function goes is to here, right? And I'm kind of trapping it by the bottom, and that's -1, -2, -3, coincidentally, -3. How high does the function go? Well, the highest the function is that point right there. And so it's being trapped between -3 and up here, right? So if I go from here to here, I'm going to get the whole function, and that's 1, 2, 3. So from -3 to +3. And does it leave anything out? And this time, when I say, does it leave anything out? Well, I can see, well, it does leave values for y out. For example, if y was -1.5, -1.5 is right here in between. And so what's happening is it's going from -3, the very lowest, to the very highest, +3, but it's leaving out these values in here. It's leaving out, see, this is right here, this is -1, -2. And so it's actually leaving out values between -2, including -2, it's not defined at y equals -2, all the way to y equals -1. It is defined at y equals -1. And so how we're going to put this is that our range, rather, our y values start here where y is -3, and we're okay with y being -3, comma, go to y is -2. So all y values, y is -2.5, yeah, there it is. Y is -2.7, yeah, there it is. Y is -2.1, yeah, there it is, right? And so remember, that's down, right, from the what our y values would be, and I don't care what the x value is, but at -2, it's open, and so I need to put a parenthesis and then union, and then we're going to start again at -1, and it does include -1, and then it went to the high of 3, and it does include 3. So there is our domain and our range. So they asked us, is it a function? We used the vertical align test. We asked about the domain since we had the graph. I like to do when I'm on a graph, the domain is the x's, how far to the left, how far to the right. And then does it leave anything out? And then on the range, that's how far down, how far up does the function go? And so that's kind of how we did it. Now they're asking us to find the domain of this function on 42. And so this is problem 42 out of your textbook on 1.1. And we're going to give a try to looking at it. I hope that you're noticing that there are square roots. And the deal with a square root is the underneath part, underneath here, underneath the square root, which is called the radical, the radicand underneath. So the whole thing is the radical, and then underneath is called the radicand. The radicand has to be greater than or equal to 0. So we know that underneath the square root, that the radicand has to be greater, so 3 minus t, has to be greater than or equal to 0. And this time we have 2 radicands. And so this other radicand, I was going to write radicand has to be greater than or equal to 0, is 2 plus t, has to be greater than or equal to 0. And both of these conditions have to be true in order for it to be in the domain. And so if underneath this radicand is negative, remember underneath the radicand you have to take the square root of a negative, then if that's negative, then the whole function would be undefined. If underneath here is negative, the whole function would be undefined. If they're both negative, it'd be undefined. So if this one was, the radicand was negative and this was positive, that value would make it undefined. If this was positive and that was negative, then it would be undefined. If they were both negative, it'd be undefined. So the only place that it's defined is where they're both positive. And so greater than or equal to 0. And so this is and. It has to meet both conditions. It's not or, it's and. And so when I solve this, I would take away 3 from both sides of the inequality. You could move the t over. That would be also right. So negative t is greater than or equal to -3. Then in order to solve this, I'm going to divide by -1. And when you divide by a negative, you have to flip the inequality symbol. I don't know if you remember that you need to flip that inequality symbol. So negative t divided by -1 is t. And then I'm going to flip the inequality symbol. And then negative divided by a negative is +3. And I'm going to graph that on the number line. And in fact, I'm going to put them on the same number line. And so that I can look at where the and is. And so here's 0, right here, 1, 2, 3. And so this is saying that t is less than or equal to, so that's this way. And so as long as I pick values for t that are here, then this one will be positive. So for example, if I pick 0, then that would be 3 minus 0 is 3. So that would be the square root of 3, and that's totally fine. If I pick -5, then that would be 3 minus -5. So that would be 3 plus 5, which is 8. That'd be the square root of 8, and that's totally fine. If I pick anything over here, like 4, then that would be 3 minus 4 is -1. That'd be the square root of -1, and that's not real. So that's the reason that this meets the condition for this one. Now I want to find something that also meets the condition for this. So I'm going to take away 2 from both sides. So this says t is greater than or equal to -2. And I'm going to put that on the same number line here that I already have. And so I'm going to come over here. Here's -1. Here's -2. I'm going to draw this arrow just a little bit more. And I wish I had a colored pencil, and I had things in here, but then they've gotten away. And so I have a pen that I can write with. And so here's -2. And so we're going to come right here, and I'm going to draw this brand new. So I have to peel something off the tip so that it'll write. And greater than is this way. And then where the and is, where the things that are and are the things that solve both of them. And remember, that's what we wanted. And I want to show you how things solve the second one. So if I pick -1, which is in this region, then that'd be 2 plus -1, which is the square root of 1, which is fine, it's positive. If I pick something over here like -3, then that would be 2 plus -3. That would be the square root of -1, and that's not in the domain. And so what I want to choose for the things that meet the and are the things that solve both of them, which are the things that go from -2 to 3. So as long as I pick those, if I pick anything outside, then it's going to solve one but not the other. And so the things where I had the overlapping between -2 and 3 are the things that make both of them okay. Like if I pick 0, then this would be the square root of 3, right? If I pick 0, and it would be the square root of 2. The square root of 3 minus the square root of 2, both of them are positive, so no problem. It's great. If I picked 1, then that would be 3 minus 1 is 2. That'd be the square root of 2. This one would be the square root of 3, so it would be the square root of 2 minus the square root of 3. Both are positive, so it's great. So the domain of the function, domain, are the values between -2 and 3. As long as you pick between those, you're fine. Okay, so we did a lovely job on those. On the next page, there's some more 1.1 examples, time permitting, I say. And then I'm making a video of them just in case there are things that it's difficult. 1.1 is a big section, and it's a review. It's not a review all of Math6A, which is our pre-calculus class, but it has a lot of review from that pre-calculus class, and all in one section. I mean, I would say that in a pre-calculus class, you probably covered it in, I don't know, 4 weeks, a month. So the absolute value of 9 is 9. The absolute value of 0 is 0. And the absolute value of -8 is 8. And so you probably know them with numbers. And probably where you're not as familiar with them is when they're variables. And so by definition, if you have the absolute value of x, that's equal to x if or for x is greater than or equal to 0. If you're wondering, what is that little box right there? It's me making some space there, and I didn't realize that it printed that box. And so it's just because I didn't want them so close together, and I didn't know how to make it blink. And then the absolute value of x is equal to -x for if x is less than 0. Now, so that you can see that, hey, that, x is supposed to take on the value of any number that you want. And I just want to show you that, hey, that this does work for these numbers that we had up here. If I put 9 in here, well, 9's bigger than 0, so I should be using this top one. So the absolute value of 9 should be 9, right? It should be the same thing. 0 is greater than or equal to 0, so I should be using the top one, and the absolute value of 0 should be 0. So, yeah. And then -8, well, -8 is not bigger than 0. So I should be using here, -8 is less than 0. So I should be using this definition. So the absolute value of -8 is equal to negative of -8, and negative of -8 is +8. And of course, it's easier with numbers than it is with variables, but you can see that this is supposed to be true for any number, right? Whereas when you were thinking about it here, you were thinking about a specific number, not any number. And so this is a statement that's true for any number. This is that same statement, but instead of using X's, they put boxes in there. Anyway, so we're just going to kind of follow that, and you can follow the box if you want, or you can follow, hi Susie. My cat just jumped up here, and she didn't go underneath the camera, and so you might have saw her tail swish by, but she's really upset. She's like, you've been gone at work all day, and then you come home and you get on your computer and start staring at a screen and talking to yourself. It's just weird. Anyway, so in here I have 3x minus 2, and so just following this, you put exactly what you had on the inside of your absolute value right here, 3x minus 2. Oh, shoot. Oh, I poured myself some water, and then where did I put it? And then right here, you do negative of that value, whatever is in here. So in this case, we have 3x minus 2. So you're going to do negative of 3x minus 2. So negative of 3x minus 2. So parentheses would be implied when you replace. So we're replacing the box, right, with 3x minus 2. So there would be parentheses there, and so I put those parentheses in. I think I told you that today. Anytime you substitute, parentheses are implied. And then right here, whatever you have on the inside, and both of those places go. See how it's just the same? So in 4 places, it's just exactly what you had on the inside. In 1 place, it's the opposite of that. So right here, 3x minus 2, and here 3x minus 2. And then just to simplify this, so there's nothing I can do to simplify that. It's just 3x minus 2. Here, I can leave this like this if I like, or I can distribute the negative, my choice. And sometimes it's better for me if I distribute the negative, and sometimes it's better for me if I don't distribute the negative. So that's half dozen each to the other. So I'm not going to this time. But I should solve these so that I have just x. So I should solve this for x. So I should add 2 to both sides. So I'm going to kind of solve this out to the side right here. So I'm going to add 2 both sides. I don't flip the symbol because I don't only flip the symbol in inequality if you divide by a negative or multiply by a negative. And then I'm going to divide by 3. And 3 is positive, so I don't flip the symbol. So this becomes x is greater than or equal to 2/3. So this is 4x is greater than or equal to 2/3. I can go and solve the other side right here. 3x minus 2 is less than 0, but you're going to notice a shortcut of not having to solve this one, because when I add 2, and I divide by 3, its x is less than 2/3. So it's just the change of the symbol. So the 2/3, and that's just less so this is x is less than, and I was making a greater than symbol, greater than 2/3. It's going to come up in calculus that we need to get rid of the absolute value symbol because of all the things that we're going to try to do. Find limits, find derivatives, and find integrals. Those are the 3 big things in the class that a lot of times they cannot be found with the absolute value symbol. So you have to get rid of the absolute value, then you can go do it. So if it asks you to find the derivative of this, you can't find the derivative because it has the absolute value. You might not even know what a derivative is, and that's fine. And so you'll have to make it into a piecewise function, then you can find the derivative. So that's the story, and the integral the same way. And so that's the reason that they start here in the review, because that's some things that you did in your pre-calc class is you got rid of the absolute value, and they're wanting to remind you how you did that. Here they're asking me to sketch the graph f at x equals the absolute value of x divided by x. So that's what they're asking me to sketch. I want you to notice the very first thing. I mean, I start thinking, okay, they're wanting me to sketch this, and not every value is an appropriate value for me to choose. It's not. So if I start picking points, and I'm not gonna pick points. It's got absolute value in it, so I'm going to show you what I'm going to do. But because I'm dividing by x there, I know that I should never pick x is not 0. So I'm just going to note that to myself. Note, x can't be 0, just so that I don't forget that. Okay. And then I want to use the definition of the absolute value. So the definition, f at x equals the absolute value of x equals, well, that's just this, right? Directly, right? So I'm just going to write that down. It's just exactly that, right? Okay. And I know you're saying, hey, you left off some of it. And you're right, I did. But don't worry, I'm going to pick it up. Oh, man, I've got some stress going. Okay, so this is x or negative x. And this is if or for. I guess I used for before. Probably came out of your book. And I've also seen if. Okay, so I just wrote that down directly from above, right? Okay, but our function that we had here, that it had divided by x. So I'm just going to come right here and I'm going to divide by x. And then what you want to do right here is you want to divide by x and you want to divide by x is what you want to do. These conditions are the same. If x is greater than or equal to 0 and if x is less than 0. And so, and now I'm just going to simplify that so that this function, f at x, that equaled the absolute value of x divided by x, is equal to, well, x divided by x is equal to 1, and that's for x being greater than or equal to 0. And negative x divided by x is equal to negative 1, and that's 4. And for x is less than 0. When I divided by x right here, and we had noted already that x can't be 0, and I had that or equal 0, I should have come right here and I should have erased the or equal to and said greater than 0, right? Because it shouldn't be equal to 0. And I should do that right here as well. And so now I'm going to graph this. So this is y equals 1 as long as x is greater than 0. And I was showing you, this is a horizontal line, right? Horizontal. I don't normally write that. I normally just think it. And I told you that I don't normally get points either, but I want to get points just so I can kind of show you. I'm going to pick 0 here, but I'm going to say that it's open, right? And so as if I would be, because I'm using this top one, right? And I'm picking 0 even though it's the boundary. So this would be equal to 1. And then I'm going to pick 1, and I'm using this top one that's bigger, so I'm going to have 1. So I'm going to come right here, and I'm going to plot over 0, up 1, and it's going to be open. And then over 1, up 1, and it's going to be closed. And then I'm going to draw the horizontal line. And I do that just so that I can get the boundary. It's hard to see that that's open, but it's open. And then same here, I have y equals negative 1. And so I'm going to have my x and my y, right? And the boundary is 0, but 0 should be, and in this case, it would be equal to negative 1, and it should be open. And then I'm going to pick values that fall into this category, like negative 1. And so that will be equal to negative 1. And so I'm going to plot over 0, down 1, over negative 1, down negative 1, and it's also a horizontal line. So that's what the graph of this looks like. You notice that x is 0. Remember, I noted that x can't be 0 because it makes the denominator 0, and so I don't have that. When you look in the back of the book, they're not going to have that point plotted right there, or that point plotted right there. They'll definitely have the open. I have that point plotted there just to help me on my drawing it. And so if you were like, well, it's a horizontal line, well, as long as you know, you got to know where it starts, right, and where it ends is kind of the deal. So I kind of, I guess, overkilled it, right, with my picking of my points. Okay, a few more examples, and then I'll put this video onto YouTube, and then I will have some dinner. My mom and dad said they were going to feed me tonight, and I keep wanting them to call and say what the story is. Okay, symmetry. There are even functions. Another way of saying an even function vocabulary you can use is it has y-axis symmetry. And so here is the graph of something that is an even function and has y-axis symmetry. When things are even functions, if the point AB is on the graph, so if this point AB is on the graph, then the point negative AB, this point here, negative AB, would also be on the graph. To prove that something is an even function, all you have to do is show that f at negative x, sorry, I had a sneeze. Am I going to sneeze again? Equals f at x for all x. So it's not good enough to show that that is true for one particular value of x. So I have sometimes people will show me that f at negative 1 equals f at 1. And that's good. I mean, that means that it might be an even function, but you have to show for all x. So you have to show for negative 2 and 2, and for negative 2.5 and positive 2.5, and negative 3.1156 and positive 3.1156. You have to show true for all values of x and not just a couple particular values of x. I'll show you some examples of how to do that. Okay, an odd function has origin symmetry, and here's the graph of something that is an odd function, and called an odd function or origin symmetry. And if AB is on the graph, so if the point AB is on the graph, then the point negative A, negative B is on the graph of an odd function. When you want to prove that a function is an odd function, you need to show that f at negative x is equal to the opposite of f at x, or negative of f of x for all x. And I'm going to show you an example of how to do that. Then there's also graphs that have x-axis symmetry. You notice that they do not call them a function. So they don't say that it's an odd function or an even function. And the reason that they don't is because if they have x-axis symmetry by the vertical line test, things that have x-axis symmetry are not functions. And so if you were talking about the symmetry, you would say it has x-axis symmetry, but you wouldn't call it some kind of a function. And for these friends, if a point AB is on the graph, then the point A negative B is on the graph. And so that they would be symmetric with respect to the x-axis. To prove that a graph of an equation has x-axis symmetry, you replace y with negative y in the equation. If the equation can be simplified to the same equation that you started with, then the graph of the equation has x-axis symmetry. Okay, so we're going to give a try to these three, and then that's it. We have 3 more problems. They're all problems out of your book. And so these are the examples from 1.1. And so they say determine if f, so they've given you a function f here in these problems. And they say determine if f is odd, even, or neither. And be sure to show your reasoning to support your answer. So we're gonna give a try to that. So I remember to myself, if it's odd, then that means that f at negative x equals negative at f at x. If it's even, then that means that f of negative x equals f at x. So I'm going to give a try to seeing what it is. So they've listed what f at x is right here. And so I'm going to look at f and negative x right in there. And so remember, when you substitute in, so I'm going to substitute in to f negative x. Remember, parentheses are implied. So this would be parentheses squared, because I like to go and fill in all the x's with parentheses. And this is raised to the fourth plus 1. And then what I'm going to plug in is I'm going to plug in negative x. So right here, negative x, negative x. Now, when you square negative x, that's negative x times negative x. I'll write it out here. Negative x squared equals negative x times negative x. And when you multiply those together, a negative times a negative is a positive. And so this would be x times x, which is x squared, right? And so this would equal x squared divided by, and the same is true for x, negative x to the fourth. That would be negative x times negative x times negative x times negative x. And there would be 4 negatives, which is even. And so that would be just the same as x to the fourth. So this is x to the fourth plus 1. And you notice that is exactly what we started with. That's exactly equal to f at x. It's exactly equal to our function. So we just proved that f at negative x is equal to f at x. So we've just proved this, which means then that it's an even function. And we've done that for all values of x, not just any particular value of x. And so thus, I'm going to say, thus, even function. F is an even function. So we did a lovely job on that one. And we're going to try the next one, and the same idea. So they're asking me if this is odd or even. And so I'm going to start off with f at negative x equals, and then I'm going to put parentheses right where I see x, divided by parentheses plus 1. And what I'm going to put into those parentheses is negative x. And then I'm going to simplify this. Well, because it's negative x raised to the 1, that's just the same as negative x. And in the denominator, that's negative x raised to the 1 as well, so that's the same as negative x plus 1. And that's not exactly the same at f at x. Now, I might say to myself, well, you could factor out a negative in the numerator and in the denominator. I want to show you doing that so that you can see. So if I do that, that'd be negative 1 times x divided by negative 1 times x minus 1. Now be careful, I have to distribute here, right? Negative 1 times x is negative x. Negative 1 times negative 1, negative 1 times negative 1 is positive 1. So the difference between the numerator and the denominator was size, right? The numerator was a monomial. And so I could just factor out the negative 1. Negative 1 times x is negative x. But the denominator was a binomial. And so I had to factor it out of both pieces. And then I have negative divided by a negative. Negative 1 divided by a negative 1, which is equal to 1. So this essentially cancels out and leaves me with x divided by x minus 1. And I'm like, well, that's not what I started with, and it's not the opposite of what I started with either. And so and I'm out of options. I mean, I made the numerator the same, but the denominator's different, and it's because of the binomial. And so this is not even or odd. This is neither. Thus, I'll say thus, neither. Okay. F at x equals x times the absolute value of x. So they're asking me, is this odd or even or neither? And so I'm going to try to find out. And what I'm going to do is to test it, f at negative x equals, and then I like to use parentheses, right? So here's parentheses here. and then absolute value, and then parentheses in there. And I know it looks really funny, but everywhere I have x, I'm going to be replacing in those parentheses negative x. So on the outside, it's negative x raised to the first, so that's just negative x. On the inside, though, it's the absolute value of negative x. So I put those parentheses to help me get it replaced, but that's what I have, the absolute value of negative x. And you might not have seen this, but I'm going to show you with some numbers. Like if I have the absolute value of negative 9, I want to convince you that that's equal to the absolute value of 9, that they're equal to one another. They're both equal to 9. And so these are both equal to 9. They're both equal to the same value, right? And so no matter what you pick, negative 7 is equal to the absolute value of 7, right? They're equal to one another, even if you pick 0. The absolute value of 0 is equal to, negative 0, right? I don't know. Negative 0 is equal to 0. And so that will look really funny. Absolute value of negative 0 equals the absolute value of 0. And that is going lol. But yeah, it's true. For no matter what x is, the absolute value of negative x is equal to the absolute value of x. And so I'm going to note, hey, that's true here. So I'm going to have here the absolute value of x. Now, I don't know if you noticed, but this part right here that I'm going to lightly circle, x, absolute value of x, that's what f at x is. So this is equal to then negative, right, because it's negative right here, and then that I've lightly circled is f at x. And then remember, woo, if this is equal to that, which is that's what I just found, right, that right there, then it's odd. So thus odd. You probably could have guessed that because you probably could have guessed that, right? Because one example that's even, one that's neither, and one that's odd. And so, yeah. Anyway, okay, those are the extra examples for 1.1. And so there we have it. I wonder if I should do the extra examples for 1.2 now on a different video. Yeah, I think I might. We'll see.